Okay, well, it's my pleasure to introduce our first student speaker this morning, who is Catherine Ross, or Kat, as she goes by many of us. She is in her final year of her PhD, working with Danny Stockley and myself on the Chicxulub impact crater, as well as the Ries crater, it turned out, and a number of different cool projects on how you can use impact craters to understand tectonics of an area, as well as the role in which shock, basically shock for the pressures from an impact, plays on the ability to date the impact itself, as well as potentially the ability to date the after effects of an impact, like a hydrothermal system. And you'll notice some cool, thank yous to NASA and a number of things up there. And one of the cool ones up there is the Barringer Crater Company, where Kat wrote a proposal to get some funding to work on this project, which is pretty neat. And that's actually the family that owns Barringer's Meteor Crater in Arizona that has their own small foundation, which is pretty cool. Kat came to us from McGill twice, both undergrad and master's, and is in her, I guess, 5th year, right? Yeah, and plans to graduate in May. And this is her AGU practice talk. Thank you, Kat.
Thank you, Sean. Yeah, so today I'll be talking about zircon, uranium, thorium, helium dating in impact craters. And I'll just draw your eye to this single zircon that has this crazy granular texture shown in electron backscatter diffraction. So zircon, uranium, thorium, helium has been used in impact crater or in tectonic settings for a very long time. It has some intricacies that complicate how we interpret the ages, but the sort of thermochronology world has a really good handle on how radiation damage, which is the spontaneous fission of uranium in a grain, how that affects the closure temperature and how helium diffuses out of the grain, which therefore affects how you interpret the ages. We could also have inclusions of fluid or of other minerals in zircon, or we can have atomic vacancies that all would affect how the daughter product, helium, is diffusing out of the grain. So something we haven't thought too much about is how deformation would affect how helium is either trapped inside or released from a grain. Deformation, either brittle here or ductile, shown in sort of this micron scale in this EBSD, or in nanoscale in these TEM images, could affect how diffusion happens in a zircon and how easily the helium can be released from the grain. And this would likely affect the age robustness. So down here, we see, common pressure temperatures of deformation of terrestrial crust. And then today I'll be talking about sort of the end member of deformation, which happens in an impact crater. So very high pressures and temperatures, very punctuated event. And the goal of this project is to look at how impact-induced microstructures affects the diffusion of zircon. So zircon, uranium, thorium, helium has been done in impact craters before, including work by Connie, a research scientist here at UTIG. This plot over here shows the different chronometers used. This is from the Chesapeake Bay impact structure. And I'll just draw your eye to the uranium lead zircon chronometer. So that's a very high temperature chronometer. And the uranium, thorium, helium age is a little bit younger than that. So this is something where if you're releasing the daughter, you may be, lowering the age, but that may be something that's interpretable as a hydrothermal system. So it's very, very useful. The zircon, uranium, thorium, helium chronometer has a closure temperature of about 200 degrees Celsius. This will be important. This is the number that we're kind of shooting for in plots that I'll show on later. So keep that in your number in your head. So the two impact craters that I'll show data from today are the Chicxulub and the Ries crater. The Chicxulub is 66 million years old, and it has a long hydrothermal system of about 6 million years. It's also very large. The Ries crater, on the other hand, is much younger, 14.8 and has a 250,000-year hydrothermal system. This plot on top shows different helium ages that have been published or are about to be published, and this normalized by impact age. And what you can see here is that our peaks are generally about 1 million years younger than the crater themselves. So again, this may be deformation-induced younging of the age. So we'll get into how I'm going about sort of looking at these diffusion kinetics. So we first classify each zircon grain by the external morphology of the grain. So these are backscatter-electron diffraction images to see if we can see any sort of textures that would sort of be a good guess of what kinds of features are there. And then a subset of the grains go to diffusion experiments. And these are our diffusion cells in Danny Sokulu's lab on main campus. And then those subset go to get characterized by electron backscatter diffraction, EBSD for short. And this will tell you about the misorientation of the grain. So, sorry. And then if a subset of the other grains will go to just regular helium dating after we've characterized the outside of the grain. So some background about diffusion experiments. We're going to be looking at a lot of plots. And so I want to kind of get everyone on the same page. We pack a single grain into a packet, wrap it in a copper, attach it to a thermocouple, put it in an ultra high vacuum cell, and then we'll heat it at a constant temperature for a set amount of time, shut that off, and analyze how much helium was released due to that heat. And then heat it again for a certain amount of temperature or time, shut off the light bulb, and then analyze the gas. Helium obeys volume diffusion in zircon, so it follows this Arrhenius relationship shown at the bottom here and on the plot here on the right. So we have temperature on the X and diffusivity, or how much helium is being released in each of these steps, on the Y. And so after doing some prograde and retrograde steps, we'll have a plot where we have each of the steps is represented by a point on this plot. And then we can fit a line through the data if it is truly volume diffusion. And then we get a slope and a y-intercept. And the linearized Arrhenius equation is shown on the bottom here. So our slope is the frequency factor. So it's this d naught over a squared. A squared is the domain size. Also keep this in mind, because what happens with the microstructures that will be changing the domain size. So this is an important term when we're looking at some of these plots on my next slides. And then the slope is proportional to the activation energy. That's, you know, how much energy is needed to actually get the helium out of the crystal. And then these two terms are what goes into how we calculate the closure temperature, which again is supposed to be 200 degrees Celsius. So that's what you need to actually calculate the closure temperature. So some possible outcomes. If the grain obeys volume diffusion and there's not too many shock features, then where did I lose our previous slide? Okay, we heat it up back and forth, prograde, retrograde. We have basically at each temperature step, we'll have some sort of helium that's diffused out of the crystals, some sort of volume, and that's this diffusivity. If it obeys volume diffusion, then it's defined by a slope and a y-intercept shown here. The y-intercept has this diffusion domain term. And this is important for the impact microstructure. The slope is the activation energy, should be the same if it's all zircon. Okay, hopefully I caught up our online audience. So there's a couple of possible outcomes that are possible. If there are no shock features, then you would obey volume diffusion and the sample is characterized by one slope and one y-intercept. If there is not interconnected damage, just a few fractures, then again, we can hypothesize that it'll obey volume diffusion and we can get one slope and one y-intercept. If we have more highly shocked grains, then you create these planar deformation features. These planar features can act as these fast diffusion pathways or highways for helium to get out of the crystal. So any part of the grain that has these features, you can envision that the helium would be released easily from there. And then if there's part of a grain that doesn't, that would be harder to release and would release second. So in that case, you would get these first sort of prograde steps defining a slope and a y-intercept, and the sort of larger part of the grain getting diffused second and defining a similar slope, but a different y-intercept. And that's sort of because of the area of the grain that you're diffusing from. Same with these granules. You have these tiny small granules. These granular texture grains are found in the highest shock metamorphosed parts of craters. And so you can envision that it's a lot easier to get helium out of a small little granule as opposed to an entire grain. So again, you would have these two similar slopes, but two different y-intercepts, and that difference is due to the domain size. This is what is called multi-domain diffusion. So you're diffusing out of one domain and then a second domain. All right, so the first data I'll show is from the Chicxulub. This grain here is euhedral. You can't really see any features on the outside, and that's confirmed by this sort of misorientation map of the internal structure of the grain. You can see that it's basically all the same color. The prograde and the retrograde steps, which are shown sort of by color here from purple to yellow, which is how much helium is released through the entire experiment. They have the same slope and intercept. And if we calculate a closure temperature, we get a nominal closure temperature that's within the accepted range for zircon. So this is single domain random walk of helium out of a crystal. This is the second example from the Chicxulub. You can see here, you have these sort of planar features that are showing up on the outside of the grain. And so those we hypothesized to be planar deformation features. And once we EBSD'd the crystal, confirmed that we have these sort of beautiful textures within and microstructures within the grain. So the green parts are misoriented by about 8 degrees from the rest of the grain. So the prograde and the retrograde steps have similar slopes, but different y-intercepts. And we have this sort of distinct rollover pattern, and something I'll have all of y'all note is that we've released less than 20% of the total gas within the crystal. So these are constrained by less than 20% of the gas. And this is indicative of multi-domain diffusion, where you have this constrained slope, a rollover, and then a different constrained slope. Also, our calculated closure temperatures are within the accepted range. So the last example I'll show from the Chicxulub is this granular textured grain. You can see sort of these little granules showing up here, confirmed by the EBSD. This is now an IPF figure, so all of these different granules are misoriented. The prograde and the retrograde steps have gentler slopes, but different y-intercepts. So this is again indicative multi-domain diffusion, where you have this long rollover. Our Nominal closure temperatures are within the range, with the first one being slightly below the accepted range. I'll also note here that these points with a lot of spread and error are because we've basically released all of the gas from the crystal. So the first grain from the Ries, you can see here, has this sort of mottled texture, and that is confirmed with the EBSD as well. This is the one from my title slide. Here we have similar slopes, but different y-intercepts again, with not a lot of constraint on that first sort of prograde steps. And this is again indicative multi-domain diffusion. Our nominal closure temperature that we calculated is for both of our fits are quite low. So if we put it all together, the two parameters we were looking at were that slope and that y-intercept, right? So on the left side, we have the slope, and on the right side, we have the y-intercept. So slope, as a reminder, is the activation energy. And what you can see here is that there's some spread, but generally we're getting a slope around minus 2.4, with a lot of spread in the granular textured grains. So with the euhedral grains, we're very constrained, no matter if the first fit or the second fit slopes. The fractured grains are slightly higher. This may be due to metamictization of the grain, and metamictization causes a volume expansion within the crystal. So there may be an explanation for that, but generally we can calculate an activation energy that's within the accepted range from other previous zircon studies that aren't shocked. So we're looking at zircon, that's great. The other parameter is that intercept. So the Arrhenius plot is also in natural log space. So a change in this axis is actually an exponential change. And what you can see here is that we have a trend of increasing y-intercept with increasing shock features. If we look at the term here, that a squared term is on the bottom. So that means a decreasing domain size would increase that intercept term. So this confirms what we were thinking, where the diffusion domain correlates to the type of microstructure we see and how far you can break down the grain, basically. And these two plots are sort of our diagnostic patterns. So now we can definitely use these helium ages and interpret them with this backing, and learn a little bit more about the thermal history of impact craters. So the second part of this project was looking at just ages of the crater. These samples are from the Ries crater. So I guess I can hide this for us in the room. Crater age 14.8, and that's what's defined as this black line here. Each of these bars is a single zircon age with its associated error, and they're colored by shock features. So the darker ones are the least shocked and the lighter ones are the most shocked. And what you can see here is that the least shocked grains give you older ages and the highly shocked grains give you younger ages. And if you take just the euhedral and the fractured grains, you get a weighted mean age that's closer to the impact age and within that range of the hydrothermal system. Whereas if you use this granular textured grains, you get an age that's not within the hydrothermal system range. So what does this mean for dating impact craters? We need to examine the microstructure in order to interpret our zircon helium age. Impact-induced shock affects how helium diffuses through these grains, and the diffusion domain is controlled by the shock microstructure, and that's what's controlling the kinetics of helium. So if you want the impact age, you need to use the least damaged grains, and if you want to sort of investigate the hydrothermal system or younger processes, you need to use the grains that are more shocked and more likely to sort of release their helium more easily. And this is important because we need to start assessing the degree of deformation in order to better interpret our thermochronology data. So we use all these different thermochronometers in a variety of tectonic settings, but we haven't yet really thought about how that feedback actually affects the age, right? So how the deformation affects our interpretation of the age. And with that, I'll take any questions.
Great recovery there, Kat. As an AGU practice talk, I presume you've already uploaded this, but are you doing the head in the corner thing, or?
I did not do the head in the corner.
Okay, so your slides will be consistent with not doing the head in the corner, but I was just checking on that. Any other questions?
Yeah, I just thought of this. I don't know why I didn't think of this earlier this week. So that longer tail of ages on the more shocked zircons, right, for Ries, how do we know that isn't continuing to be the low grade hydrothermal system tailing off?
It could be, right? So with the granular grains, we calculate a closure temperature that's not 200 degrees. So for granular textures, you may be able to use zircon to capture 100-degree Celsius fluids or a long-lasting hydrothermal system, an 89-degree hydrothermal system. So that's something that we need to constrain, but it is still useful, right? Like the shock microstructures can tell us more, but you need to actually know that they're there. So you can't just go and get some helium ages and then expect to be able to date a new crater, for example, without looking at the different microstructures first. I hit the meeting control, so I can't see the chat. Okay.
Nothing in the chat.
No.
All right.
Thank you.
Just quickly introduce Shuai Yan here. Shuai's been working with us for about 3.5 years, 4.5 years, 5 years, 5 years. And we'll be finishing up in this coming year. He comes to us from the University of Science and Technology in Beijing. And he's been doing a lot of work looking at Princess Elizabeth Land, which is this, been until recently a relatively unexplored area of Antarctica, and in particular, a very interesting subglacial lake that has been found there. So with that, Shuai will be talking on Monday at the near surface geophysics section.
Thank you. Thank you, Devin. Can you hear me?
Yes.
Cool. And thanks for the great talk, Kat. That's a really high bar. So thank you. All right, let me real quick switch to my presentation. Going to reshare this. Okay, what's in the registry? All right, cool. It's my turn. I'm Shuai Yan. I'm a graduate student here at UTIG, working with Don Blankenship and Duncan Young. In this talk, I just want to share our recent work using airborne geophysical survey to study a wet spread subglacial hydrology system in Princess Elizabeth, excuse me, Elizabeth Land, East Antarctica, PEL. Okay, so where is PEL and why do we care? What should I spend this listening to this graduate student? The overall location of PEL is shown in the map on the left. Oh, I should go over to the map. Yeah, it's shown in the map on the left. Is this part of East Antarctica? And on the right, you can see the map of data coverage of Batmap2, which is a data set for Antarctic basal topography and ice thickness. And you can see PEL actually represent one of the biggest gap in our data coverage in Batmap2. When we put together Batmap2, was it 8 years? No, it was 8 years ago. We simply didn't have any data in PEL. So that's a motivation for UTIG to coordinate airborne geophysical surveys in the past few years. Our survey platform was built on a BT-67 aircraft, and it houses instruments such as radar, gravimeter, magnetometer, altimeter, and optical camera. And we do have multiple GPS antenna on board, which provide geolocation and time record for our data series. And all the instruments are controlled by a central integration system. And here is a map of all the survey profiles we have done in the past 6 years in PEL. This new data set would provide measurements of basal topography, the thickness of the ice sheet, information about the subglacial hydrologic condition, and the tectonic context of this region. And my project has been focusing on the subglacial hydrology in PEL. The motivation for that is those water bodies underneath the ice sheet, they can interact very closely with the overlying ice sheet, and they may hold very valuable sediment record of paleo-environmental changes, ice sheet evolution, and hydraulic activities in the past. So that's the motivation for my study, but how do we do that? Well, in order to study those water, we need to first identify them. We need to know where they are. Remember, we're talking about water that is covered by 3,000 meters of ice. So we need to know where they are in the first place. And to do that, our radar is a very powerful tool. Essentially, we're looking at 3 criteria of the basal reflection in our radar measurement. So that's a reflection from the bottom of the ice sheet. The first one is subglacial hydraulic potential. The expression is given here. It is a potential energy caused by the combination of gravity and the pressure from the overlying ice sheet. The second one is basal reflectivity, which describes for a given amount of incidence energy, how much of it can be reflected back. The third one is basal specularity, which describes for a given amount of reflected energy, how much of it is toward the incidence angle. My advisor, Don, would say, and I quote, just imagine a mirror versus a carpet. The mirror would have much higher specularity than the carpet. So yeah, those are the 3 criteria we depend on to identify water from our radar. If we observe, close to 0 hydraulic gradient, or i.e. constant hydraulic potential, enhanced basal reflectivity, and specularity, altogether, they indicate the existence of water beneath the ice sheet. But sometimes we see high reflectivity. However, the specularity is not as high as what we would expect for water. And that would indicate sediment, water-saturated sediment beneath the ice sheet. So that's how we identify water under 2 miles of ice sheet. After that, we can study the interactions between those water bodies and the ice sheet by looking at the inglacial stratigraphy. We can use the magnetic anomaly to study the tectonic context, and then we can use gravity to invert for the depth of the water and the thickness of the sediment layer if there's any sediment present. So with this method, we have been able to identify multiple water bodies in the interior PEL, as shown in this map, and the map later in just a minute. Among all the identified water bodies, the biggest one is referred as Lake Snow Eagle here. Snow Eagle is a name for the aircraft we used in the survey. So we're trying to acknowledge the contribution here. And for example, for Lake Snow Eagle, you can see that we observe enhanced reflectivity. However, specularity is not as high as we would expect, which means there is sediment present around Lake Snow Eagle. And I will use Lake Snow Eagle as an example to show you how we can further study its properties in just a minute. Here's more downstream region. We identified a few more water lakes, which is nice. It's a web spread hydraulic system down there. And here are some data products over the Lake Snow Eagle region. Surface elevation of the ice sheet, the basal topography measured by our radar. From the basal topography map, you can see that Lake Snow Eagle is sitting in a deep subglacial trench in the about north-south direction. And free air gravity, there is a short wavelength negative signal above the water, which reflect the density difference between ice, water, sediment, and the rock. And Bouguer gravity and magnetic, they do not correlate with our basal topography at all, which indicate a possible geologic boundary in this area. So to test that hypothesis, we run a few simple 2D geophysical models, and we use magnetic to constrain the result. Now, I won't bother you with all the details with the model. The takeaway answer is, yes, indeed, Lake Snow Eagle is sitting on a compressional geologic boundary. That's the takeaway answer. Then we run another series of models about the bathymetry configuration. And there are two takeaway answers. The first one is, yes, there is sediment present. So we now confirm the existence of sediment from radar and our potential field data, two independent data sets. And the second takeaway is that the slope of the bottom of Lake Snow Eagle is different from the surrounding bedrock. So we cannot simply just project the slope and say that's the water depth. No, we cannot do that. We have to use gravity to estimate the water depth and the thickness of the sediment layer. So we did that, and here's the result. Here are some cross sections of our geophysical models, and on the right, there are some interpolated map of water thickness and sediment thickness. We confirm Lake Snow Eagle to be one of the biggest, and the typical water depth is about 100 meters. The size is about 40 kilo by 10 kilo. So that would be 25 miles by 6 miles, I guess. And there's sediment at the bottom of Lake Snow Eagle. Typical sediment thickness is about 100 meters. Another thing, something I want to point out about the sediment is that we run a quick estimation of the sedimentation rate in this area. The takeaway answer is, for such a thick layer of sediment, it would actually require periglacial or even pre-glacial sedimentation mechanism, which means this sediment here may provide record of paleo environmental changes probably even before Antarctic glaciation, we provide record of the initiation and evolution of East Antarctic ice sheet. And if there has been any hydraulic activity happened in the past, there may be a record of it in that sediment. So the project I have been working on in the past few months actually is about the in-glacial stratigraphy over American snow eagle. And I do have a poster for that in this year's AGU. So if you're interested, please check it out. The poster number is attached here. All right, to sum up, we were able to use airborne geophysical survey to identify a widespread subglacial hydrography system in the interior PEL East Antarctica. We then investigate the geologic context and the bathymetry. And for the biggest one identified, we confirm it to be actually one of the largest subglacial lakes in Antarctica. And we acknowledge that it may hold very valuable sediment record. And now we are studying the interaction between those water bodies and the overlying ice sheet. And this study is a part of a big international project. So I just want to say thank you to every one of our coworkers. And with that, I'm happy to take any questions. Thank you.
Very good talk. I have one question. Just curious, from your previous slide about water and sediments. There's two polygons. They are similar, but not exactly the different. I want to know how you draw those polygons. I thought it is based on the three plot you mentioned earlier.
Good question. So that question refers to essentially the outline of the sediment versus the water. They are different, as you can see in here. First of all, this is the first study. Is this a estimate? So it's an estimation. It's not 100% accurate at all. How do we derive this outline? Short answer is radar. Like I mentioned, there is a difference between water signal versus sedimentation signal in our radar, and we can see that. And we can also see that in our inversion models, as shown on the left here. I built a few models with the water that expand all the way to the edge, and that didn't work out. So again, we are using two independent data sets to confirm and distinguish water and sediment. I hope that answered the question. Yes.
I guess I have one quick comment, which is when you hit bed map 2, because you have a general audience for your session, you might just tell them what that is, because you'll probably have some people who won't know. And then the question, what's the estimate of the timing of when this became ice covered? Do we have some idea of geologically when that would be? And I guess the counter to that is how did you come up with an estimate of sedimentation rates subglacially to say that it needs to be either peri or pre-glacial?
Yes, so the question is essentially twofold. One is what's our estimation of, you use the term ice covered, but I would prefer the term of the age of this lake, because for now we think the lake is pretty young. It's younger than definitely younger than the ice sheet above it. So I'll talk about that later. And the second part of the question is that how did we estimate the sedimentation rate? So there is, okay, assuming all the sediment was deposited after the ice sheet was there will only be a very few sedimentation mechanism, either carried by subglacial water discharge or carried by the overlying ice sheet. And there has been a few studies estimating each of them for, in general, or for the subglacial Lake Vostok, which is the biggest in Antarctica. And assuming our sedimentation rate is at least on the same order with all the previous studies just mentioned, no, they're not enough. They're not even close to enough. So that means there must be something already there before the ice sheet came in. And refer to the age, which we will cover in the poster. But from the in-glacial stratigraphy signal, we can see how the water communicate with the ice sheet. And that can only be traced back to about, I would like to say 10 or 15,000 years ago. No signal before that, at least from our in-glacial stratigraphy point of view. So that's why I said it is probably much younger than the ice sheet. So I hope that answered your question. Is there any question on Zoom?
Well, if no other questions, thanks to Kat and Shuai for entertaining us this morning, and good luck in New Orleans next week. Thanks, everyone.